So this goes into just a little more detail, that when you look at the pleasingly parallel case, you have pleasingly parallel over users. That's the Google search application. Lots of users doing independent searches, and you have the parallelism over usages. That could be the chemistry docking calculation. You have a given job run by a single user, but it might look at a million different protein dockings to see which ones are the most successful. So they're two important pleasingly parallel problems. And the long tail of science is like the long tail of search, namely that's lots of users each doing a small amount of work. And that differs somewhat from big science, although with the big science, which is like particle physics, it has a major pleasingly parallel application called parallelism over usages, namely parallelisms over and analyzing each event separately. So the pleasingly parallel in the map-reduced languages is called map-only, and when you dock multiple chemicals, you can actually use MapReduce, and people have shown that works well. And you just run each chemical as a different map task. This slide here, there's a well-known computing research pyramid. At the bottom, you have the long tail. Here you can call the long tail laboratory clusters. Here you have universities, mid-sized systems. Here we have the national infrastructure. And here we have the very top petascale and exascale. And clouds are most of the currently focused on this big, fat middle piece here. Or in fact, they're focused at the bottom because they're trying to take your desktop and provide a seamless extension of the desktop into the cloud. So they're trying to show you how you can take this purple desktop computing and build it automatically into the cloud. Eventually, clouds will probably extend further up there, but at the moment, with current virtualization and technologies, they're not so good at the very highest end computation, which require low latency and no overheads. Virtualization produces problems because the virtualization of the network means that you can't guarantee nodes are near each other. Also, virtualization is a software wrapper and creates overheads, which many people are trying to address, and I suspect will get better. If you actually virtualize position, that will not get better by working on the hardware, on that software layer. You will just need to do a different form of virtualization to allow nodes to be created near each other. So this tries to summarize in more detail the difference between high-performance computing, which I've stressed many times now. We can do it actually in sort of map-reduced formalism. The maps are just corresponding to processing a set of particles or a set of mesh points, and they need to use point-to-point, I mean node-to-node MPI communications, which tend to be rather small and need low latency. In clouds, we tend to run MapReduce, which is which actually is more fault tolerant, somewhat easier to use. And the map-only case, we already mentioned, that's a pleasingly parallel case. And then in between HPC and cloud MapReduce, we have iterative MapReduce, which tries to do results which lie in between MapReduce and HPC, and actually give you interoperable way of using either HPC or MapReduce. One important comment there, which is relevant to this X-informatics class, is that for X-informatics, we tend to be doing data-intensive applications. We do simulations. That's quite important if we're trying to there are some simulations of importance in X-informatics. If you do material informatics, you're going to do supercomputing to design new materials. But if you do most data-intensive problems, you're going to doing things like clustering, support vector machines, and algorithms like that, deep learning algorithms. Those applications can be parallelized, but they do not look like, they do not have the same structure. as a typical simulation because they don't have the geometric structure, which tends to mean that you have to keep, when you do your geometric decomposition of a large-scale simulation, you want to keep nearby points near each other, and then you exchange messages between those nodes, and that's what is your parallel algorithm. If you do a data-intensive application, you're going to have some matrix, and you're going to do parallel matrix algebra. There is no locality between the different rows and columns of a matrix typically, and so you do not have that constraint. And so your messages are larger. They tend to be global messages, gather, so-called all gather or all scatter or all reduce and or broadcast. And those tend to be, because they are large messages, they don't have the same latency constraints. So you can actually run them on modest latency networks. And you need to actually worry about optimizing those problems for large messages. And there's a very famous approach in data mining called expectation maximization, and that is actually very good on clouds and very suitable for iterative MapReduce. And we have looked at particular clustering and multidimensional scaling. Judy Chu, who teaches the cloud course, has done a lot of work in this area. And some of the topic determination algorithms like latent Dirichlet allocation used in information retrieval and text mining also can be done with algorithms which have this structure with large messages, not insensitivity to latency. Here's a nice example of what I was expressing earlier as to one of the dreams about clouds, and that is the so-called datascope. This used iterative MapReduce or MapReduce at the on the cloud. Then it used Excel as a front end, and it allowed your users to run giant Excel jobs where, unbeknownst to the user, the giant job was actually sent off to the cloud, and the only thing that was sent back was what the user required. And so this is obviously a very powerful model, and I expect this type of seamless transportation to the cloud of one's processing will get more and more common.